Welcome. So today we're going to talk about antiderivatives, which are the opposite of derivatives. Well, not the opposite, the backwards derivative, sort of. Anyway, we'll talk about the formulas, then we'll give some examples so you'll know what I mean, and then we'll do something called initial value problems. We've already talked about these. They're a kind of differential equation, but they fit well in the section of antiderivatives, so we'll do it again. Here are half the formulas. First to note is this. This means the antiderivative of f of x. Because think about it, what is the notation for a derivative? F prime? How do you do an unprime? You could put a minus 1, but then it gets complicated, there's too many rules. So what they actually use is this big S. It's called an integral sign. So it's the integral of f of x dx. So we can say it this way. It's the indefinite integral of f of x dx. The dx is sort of a placeholder. It's like a bookmark, or actually more like a bookend at the end of a set of books. It tells you where the end of the thing is. It's important for a lot of reasons. When we get to u substitution, it becomes absolutely critical. Right now, it's just a part of it. It's like grammar. It's like putting a period at the end of the sentence is useful. Does the period really do anything? No, it just serves the end of the sentence. And this serves the end of the integral. So the first one, the integral of f of x plus or minus g of x dx, is the integral of the two pieces separately plus or minus just outside. That's just like derivatives. Derivative of something plus something is the derivative of the first plus the derivative of the second. Antiderivative of something plus something is the antiderivative of the first plus the antiderivative of the second. It works just like with derivatives because they're doing it backwards. Here, the integral of a number times a function, you pull the number out. You can if you want. It's no problem. That's just like derivatives too. Now let me give you an example of what I'm talking about. What we're saying is an antiderivative is, like, for example, suppose I have, let's think good, 3x squared. Well, what I'm saying is, what function's derivative is 3x squared? So what is this? This is x cubed, because x cubed's derivative is 3x squared. Now the thing is, that's not the only choice I could have done. I could have done x cubed plus 5. Why? Because what happens to the 5 when I take the derivative? It goes away. So, it could have been 2, it could have been 7. So usually for these which are called indefinite antiderivatives, we put plus c. C meaning any number you want. Get another example like here. The antiderivative or indefinite integral of x to the n dx this is the opposite of the power rule. 1 over n plus 1 times x to the n plus 1 plus c. So as an example there, suppose we know the derivative is 2x. What's the antiderivative? Hopefully you now know it's going to be x squared plus c. Because the derivative of this, the c goes away, and the derivative of this is the 2x. A couple more. Since we know these with actual derivatives, we're just going backwards. The integral of e to the x dx is just e to the x. Since it's indefinite, it's plus c. If I put an mx plus b up here, instead, there's a chain rule involved, but it's simple enough we can just do it by brute force. It's 1 over m times e to the mx plus b. Plus c, of course. Now, a couple more. Notice that this rule here has a little bit of an issue if n is negative 1. Why? What's negative 1 plus 1? We get 0. 1 over 0. We got a bad thing here. So this is when x is not negative 1. When x is negative 1, we have 1 over x. We have this rule right here. The integral of 1 over x. Well, we've seen that before. The derivative of something is 1 over x. What's the function? The natural log of x. But I'm putting actual absolute value bars here because we could actually do this function on the positive or the negative side of the axis. So we better be prepared for it over here. A couple more. The sine of mx plus b. It's the 1 over m. That's going to be cosine of the thing, and then the 1 over m. You don't have to worry about that much, but the truth is, notice the minus sign here. These are antiderivatives. The derivative of the sine is the cosine, but that's not what we're talking about. The antiderivative of the sine is the minus cosine. Why? Because the minus cosine's derivative is going to be minus, which makes plus, sine. It's easy to get a little lost here. Just remember, the derivative here, the derivative of here, is the thing inside the integral sign. This one's derivative is in here. This one's derivative is in here. So we're just basically going backwards. Let's try it. Here are two. Try them out. I'll give you a couple seconds. Okay, hopefully you had time to pause and actually solve it. I've got two things here, that minus that. So I'm going to break this into two. You might be able to do it all at once. Also, there's a 4 in front of here. So we have that. Now, square root of x, well, first of all, this one here is easy. It's 1/4 x to the 4th. I'm going to say it's plus c. But when you have more than one integral, you've got to worry about your c. C is not actually a number, it's any number. So if I add any number here and I subtract any other number, they don't cancel out. One number plus an arbitrary other number, or minus an arbitrary other number, they don't necessarily cancel. You just get any number you want. So usually, regardless of how many indefinite integrals you have in a row, you're going to have the plus c at the end. One thing now, what about the square root of x? Well, the square root of x is actually x to the 1/2 power. So using the rule, it's going to be 1 over 1/2 plus 1 times x to the 1/2 plus 1. So let's simplify that as 1/4 x to the 4th minus, that's 3/2. It's going to be 4 divided by 3/2, x to the 3/2 plus c. I don't like having a fraction in a fraction. Fortunately, there's a way to fix that. A fraction at the bottom is the same as multiplying by the reciprocal. So I get 1/4 x to the 4th minus 8/3 x to the 3/2, and then plus c, because it's indefinite. You may be wondering, well, what about the definite integrals? We'll get those later. How about this one? Again, there's a plus here. This is going to equal the antiderivative here. Our rule for that was complicated, but it's only complicated because it's got an mx plus b. Here's just a 1 inside. This is minus the cosine of x. And this one is the plus the sine of x. And then, hopefully you realize there's something I missed. What did I miss? I missed this plus c because it's an indefinite integral. Now, getting frustrated by this, how about definite, cases? An initial value problem is a differential equation with initial condition. So like this. It's like an indefinite integral, except we're definitizing it. We're giving a specific value. I want the function whose derivative is that. Using our rules, it's going to be 1/2 e to the 2x plus c. But if I know when x is 0, I get 1 over here. Plug 0 in. This is 1/2. I'm going to get f of x is 1/2 e to the 2x plus 1/2. Hopefully that makes sense. I'm going to go fast through this one, but I want the derivative of these two things combined. I can do them separately, because that's what a plus does. But there's actually a trick to this one. Look at it. See if it looks familiar. Or maybe it looks a little better if I do that, 1 times that. This is a product rule. The original function is x e to the x plus an arbitrary c. If x is 0, that makes this 2. That means the c better be 2. There you have it. Try them out. They're not as bad as you think. Until next time, this is Dr. Jim.